I had no idea that you can have so much fun with an S3 Verge. Today, we jump into heavy BIOS modding. Instead of Hue or the HXD hex editor, we move to Ghidra for the logic, call GIMP for the pixels, and pop the mystery of how to add an image splash screen to this Verge. And now I have used enough assembly opcodes in my intro. We are also going to use a few tools that I've developed specifically for this project, and I'm thinking to create a dedicated website for the S3 Verge, because there is so much more to discover about those chips. And that is why I'm happy that Porkbun reached out. I actually used Porkbun to set up s3verge.com for this project. Hopefully, with this site, the S3 Verge will finally be known for more than just being the world's first 3D decelerator. A lot of places lure you in with cheap promo prices and then skyrocket the cost when it's time to renew. Porkbun is different. They sell most of their domains at cost, so your price stays low and predictable year after year. They also don't nickel and dime you on your way to the checkout. Usually you have to pay extra for things like Whois privacy and SSL certificates. At Porkbun, those are free with your domain. You even get free trials for web and email hosting right out of the gate. It's no wonder they are top rated by Forbes Advisor and USA Today. Once you have your domain, you can manage your DNS and hosting in one clean dashboard. And if you do run into an issue, they have real human support available 365 days a year. So, if you have a project that you have been sitting on, grab your domain at porkbun.com. Use my link and the code in the video description for an extra $1 off your next domain at porkbun.com. So how did this all start? Well, the first video that I made about the S3 cards recently was about the Trio 3D. This chip was on that card. It is a one-time programmable Holtec chip, and the BIOS has a size of 32 kilobytes. However, when I read this chip with my programmer, I got 64 kilobytes. And this is not a surprise, because this is the HT27C512. So this is a 64 kilobyte EEPROM chip. I wondered if we can do something with the extra space. And this is where the rabbit hole started. On the left side is the Verge, on the right side is the content of the Holtec. This is the Trio 3D, which you can see here, and on the left side this is the Verge chip code 375. So the Verge we have seen has 32 kilobytes, and we go down to 7FFF, this is 32 kilobytes, but the Holtec goes down all the way to FFFF. And this is interesting because the checksum of the Verge is the last byte, but here on the Holtec it is not set at all. Is it the coincidence that it is FF? Let's see what happens once we reach the same address here as on the Verge, and you can see that here is no data, but there is a last byte that is set. So the checksum most likely is this one, and the rest of the chip is just blank. It's not used. So I was curious, how does the CPU know where to look for the checksum? And after a little bit of searching, well, there's an answer to it. Both of these BIOS files start with 55AA, and this is a magic code to tell the CPU, this is an option ROM, please load me. This could be a controller, this could be XT IDE on a network card, or the BIOS on our VGA card. And in both BIOS files, this magic number is followed by the third byte, and this is the size indicator. So 40 means 32 kilobytes and 80 means 64 kilobytes. So I'm curious now, if I change this to 80 in the Verge BIOS and move the checksum to the end of the file, what will happen? Let's try this quickly, and then we'll dump the BIOS one more time with NSSI. So 80, now I'll copy the entire file and just paste it at the end of the BIOS again. So paste insert, and now we should also have the last byte here should be FFFF. There we go, FFFF. Let's remove our checksum from the middle of the file. So we'll just zero this out, and it follows the same pattern as here. And all the new bytes I will set to FF. At least we can see that this is the new block that we added. So now I'll flash this to an EEPROM chip and let's see if the Verge posts. And will it post? Yeah, yes, here it is. We have now 32 kilobytes extra, and why do I know that it works? It works because of the checksum. If the card wouldn't be able to access the new 32 kilobytes that we added, it wouldn't find the checksum and the card wouldn't post. Now we can go into NSSI and dump the BIOS one more time, and I believe we should get a 64 kilobyte BIOS now. And now we get 64. Okay, so here it is. We successfully doubled the size of our BIOS for the Verge. Now we can figure out how to get a splash screen into that Verge. But first we have to talk about the image that we're going to store in the ROM. This is not as easy because you can't just take a JPEG or a PNG file and copy it to this chip. First of all, even an image like this, which is just black and white and has a resolution of 1024 by 1024, already consumes around 150 kilobytes. We only have 32 maximum, and we still need to store a little bit of extra code to display the splash screen. So yeah, this is not an option. We have to lower the resolution and convert this image into something the BIOS understands and can display. And the resolution that worked best for me to utilize the space was 192 times 160. Now this is not a perfect square because we also have an issue with a skewed resolution. I'll not go into details, but we have to compress our image a little bit vertically. I don't want to work with this image. I created another one which looks like this. You can use any image that you want. You just have to follow the exact same procedure that I will show you right now, and then it should work. So the first thing we want to do is we want to compress our image. We can do this in GIMP. We just scale the image and we say 192. We have to break the log for the ratio, and then we say 160. So our image is now super small, and you can see it's a little bit compressed vertically. Next, we have to convert this picture into an indexed image. So I can go to Image, Mode, and then pick Indexed. And because this is a colorful image, we are going with 256 colors. Yeah, you have seen the title image. We'll put Lara on the ROM file as well. So that is why we are going now with 256 colors. So 256, leave the rest as is, press Convert, and this is it. And then we should get a color map of our image. So GIMP created now this color map, which we also need to transfer to our ROM chip. This is basically a lookup table for the ROM to know what color which pixel has. And now we can export this image, and we should get two files. One is the image data and one is this color palette. So let's go to Export As. We have to pick a raw image data, 3dfx Verge. Okay, export. Now it asks us how to export the image raw data, and we just leave it as is. This is what we want, and this is it. And here are our two files. We got the data and the palette. Now if you hover over this file, it's 30 kilobytes. So this is because of the 192 times 160 resolution. And here is our color palette. If this is not 30 kilobytes, you just go back to GIMP and you say flatten image. If you press flatten image, it basically removes the alpha channel, which might be included in your image data, and then you just export the file again and you should get 30 kilobytes as we did here. So once we have these files, we need to do something with the palette. If we open the palette in a hex editor, you will see 3 bytes per color, and in total you will have 768. 3 bytes per color means 256 colors. So 000, this is black, then it's a little bit grayer and it gets lighter and lighter until you're reaching white. The issue with those values is that the Verge cannot read it. Simply said, we have to divide every value by 4. But we are not going to do this manually. Go to my website, there is a Tools menu option, and look for the Verge BIOS Toolkit. So in here you will see the PAL to VGA palette converter. And here we can just upload our palette. This is already the converted one, but it looks very similar to the one that we saw in GIMP. And you can download the converted file just from here. And now we can compare both files. On the left side is the original one we got from GIMP, and on the right side is the new output file that you got from my website. They're basically the same size, but you can see that, for instance, white has changed from FF to 3F, 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 And the difference really is that instead of setting all 8 bits, we only setting 6 bits. And this is a limitation of the RAM duct that's on the Verge. We don't go into details, but this is what is required to make this work. So our palette is done. Our image data is also complete. We don't need to do anything with this. Now we can fire up Ghidra. I haven't spent much time on it, so yeah, let's see how this goes. First, we have to bring our file into Ghidra. Here is the BIOS file that we are using. And we have to make sure that we are picking the right configuration here for decoding the file. So we need definitely a little endian. This is one thing. And we need 16 bits for the size. And I think we should pick x86 real mode 16 size. So 16-bit, little endian. And this is default. So this is what we are picking for this configuration right now. And here is our file. Number of bytes. Yeah. 64 kilobytes. Before we dive in, let's have a look on the right side. Here is my hex editor. When Ghidra opens for the first time, it may not look like this. You have to find the windows and arrange them so that it's best for you. So I have the listing on the left, then I have the bytes on the right. You can access all these windows here through the window menu. How we will structure this, I want to have the splash screen all after 8000 or 8000 address in hexadecimal. And we have to add 3 separate parts. 2 we already know. It is the VGA color palette for the image, and it is the image data itself. The color palette requires 768 bytes, and the image was around 30,000. And the third component is the actual code that will display the image on the screen. And for the code, we reserve from 8000 till 8100. So this will be our code block. Then we have 8100 down to 8400, which is till here. This will be our color palette. And from 8400, we'll have the image data. Now we just have to make sure that we can edit this. And let's paste it. Yes. And here is our color palette now in the code. And it goes till, here's the last one. Perfect. So now we can copy the image data from 8400 and paste. Okay, so this should now go almost to the end. It should not override our checksum. So we have some places here now that are still untouched from FC00. And our checksum is here at the bottom. So this is okay. We almost use all the free space. And now what is left is, where is it? Here's the code that is left. So this is the code that we need. Now we're not going into the details what this code here is doing. I'll just copy it right now. This is the entire code for displaying the image. I did use AI to generate this, and I have to say it was not always easy. So now that this is all out of the way, let's think of how to inject this image display in our current boot process. Right now, the card shows us the text splash screen when we power on the system. And I'm pretty sure you have seen many cards doing this. So you see which card you have, how many megabytes you have, and so on. So this is coming from the VGA BIOS. And we also should have this encoded somewhere here in our BIOS. Now, I can't read this yet because, well, oh, here it is actually. This one got decoded. So let me decode the entire BIOS file. So I select everything and I press D. So here is a text. So you can't see everything here, but we can go to Window and look for defined strings. And then a new window pops up, and here we get the strings that Ghidra found in our file. And here is our text. I think this is the one that matches exactly what we see when we power on the system. So this is our main text that is shown on screen. Let me bookmark this. Splash. Okay, so now we have a bookmark here. Now we can always jump to this specific location. So the idea is to show our image right before we show the text. And now we need to figure out where this text is referenced, because usually it should be referenced only once, right when the card shows us this text on the screen. And we can see that this is at address 0045. We can fire up the search module by pressing S, and we just paste in our 0045 address, and you see the byte sequence is flipped. Most likely because we picked little endian when we configure the project. That's why these things are important. So now let's search. And we have 3 occasions where we have this byte sequence. So let's just start from the first one. What I've learned in the very short time that I played around with Ghidra is that in order to be successful, you need to understand what's happening around the code that you're looking at. Right here, I can already say, okay, we have an add instruction. This is not really something that we are interested in. We want to move whatever is at address 45 into a register or reference it, have the address somewhere stored. We're adding here, so I don't think this is something that we need to worry about or even investigate. Then let's continue with the next one. This one is at AAC. So this one here is a call to another block in the file. Now we have 4500 here, which does look like our memory address, but addresses are relative. So you do not reference the address directly. You're giving information how many bytes you have to go back or go forward to find the specific location you're interested in. We are not interested in this one because, well, it is a call to another block. We're looking for our string that is being used. Okay, and then we only have one more location, and this is this location. And here we're finally moving. So I think here we most likely reference our string and put it in this register, SI. Let's assume we have our string that is referenced here, which most likely then will call this function for displaying. Well, this code block is right here, or this function is right here. And yeah, this one looks like it does display our text because I think this is text mode. So this one will output the text on the screen. Great, so we found the function that is displaying the text. Now we need to figure out who is calling this function because, well, if we could replace the function call, instead of showing the text, we'll show the image, and then our show image code is going to continue with the show text code. This is what I want to do. Okay, so let's figure out who is calling this function here. And you can do this by show reference to function. And here is one location, 13CB. Okay, and here's our function call. So instead of calling this, I want to call our splash screen method. So let's first bookmark this and also add the function call in here that we have this for later. And now let's change this to the code that is sitting at 8000. But I cannot just type 8000 in here. We also see that this doesn't match. We have to use the patch command for this instruction. So here you have patch instruction. We have our smoky dragon trying to help us. Okay, and here we just get rid of this offset. It's at the beginning, and we just write 8000 in here. This is it. And this should be now our, well, it's now a sub-function 8000. So let's double click this. We should go to address 8000. And I think this is already correct. It's just popped up. So yeah, and this is our code 601E, 0E, and so on. This is what we copied before. Here's our color palette, and here's our image data, I think somewhere, and so on. So it does reference the correct location, but now we need to make sure that we close the loop and call the original method once we are done. Otherwise, we just get stuck on the splash screen. And what most likely will happen is after the timer is running out, the image disappears, and then we'll get stuck on a black screen. So this is the call now we need to adapt, and this needs to go to, it's here on the bottom right, 4803. So we'll do the same thing again. We just say patch, and we want to go to 0x4803. This should be now closing our call to whatever was called before. So this is the method that shows the text splash on the screen. And remember, we had this one here before. It's here again. So definitely we are continuing exactly there where we wanted. We injected our image splash screen. That's cool. Yeah, and this is more or less it. So we have done almost everything except for our checksum byte, which is here at the end. But we're not going to adapt it here. We'll just export the file now with all the changes that we made. And then we use the tool that I have on my website to fix the checksum. So we are exporting the program, raw bytes, and we export it as Verge Splash. And that's it. Don't look at this. This is something for the future. But now we look at the VGA BIOS checksum fixer. And here's the file we just created. Open. And we see that the checksum 5.6 is invalid and the correct one is 7C. Just download and let's see if we get the image splash screen right before the text splash screen of the Verge DX. And here's our fully packed BIOS file now with the image data and everything and the new checksum. Okay, moment of truth. Let's see if we get our image splash screen as the first thing that happens on the system. Okay, let's see if it continues. After 5 seconds, we should go to the text splash screen. Yeah! Nice. Okay, cool. Yeah, and there it is. Now you can replace the image with anything else you want. The only thing that you need to do is you need to copy the color palette and the image data. So yeah, let me know if you're going to attempt this with your Verge. I'm not done with this card. Now we have to overclock it and of course play Tomb Raider on that card, but this is something for another video. And this is all I have for you today. Thank you Porkbun for sponsoring this video. Thank you to all my Patreons and all the people supporting this channel here on YouTube. If you want to become a supporter, please head over to Patreon or join directly here on YouTube. And of course, let me know what you think about adding splash screens to old S3 Verge graphic cards, or maybe to S3 Trios later on as well. Then I hope I will see you in my future videos. Take care and bye bye.